If you pour a glass of water, it splashes instantly into the sink. Pour a jar of cold honey, and it resists, slowly pulling itself downward in a thick ribbon. That difference comes down to microscopic friction between layers of liquid. This diagram illustrates exactly what happens when a fluid moves over a solid surface. The layer of fluid directly touching the boundary comes to a complete stop. As you move upward, away from the boundary, the fluid's velocity increases, creating a velocity profile defined by vectors u and u plus du. The difference in speed between those microscopic layers creates friction. In fluid mechanics, we call this shear stress. It is mathematically proportional to the velocity gradient, the exact slope you see here along the y-axis. This graph plots how different substances react to that shear stress. Water falls under the Newtonian fluid line, showing a perfectly linear relationship. But look at the ideal plastic line above it. It requires a specific amount of initial force before it even begins to flow. Fluids also have unique molecular cohesion. This diagram shows the capillary fall of mercury. Instead of climbing the walls of the glass tube, surface tension pulls the mercury downward, creating a highly specific 128-degree angle of depression. Whether a substance flows freely, needs a push to start, or depresses inside a glass tube, its behavior is governed strictly by these molecular interactions and internal friction. When we stop the flow and look at fluids at rest, the rules change. A static fluid applies its weight evenly, pushing out in every possible direction. This diagram demonstrates Pascal's law in action through a hydraulic press. Because the confined fluid transmits pressure uniformly, applying a small downward force on the narrow plunger on the right generates a massive upward force on the wider ram on the left. This highlights the hydrostatic law. As noted in equation 3, pressure variation in a downward direction is exactly equal to the specific weight of the fluid. The deeper you go, the heavier the fluid gets. This differential U-tube manometer measures the visible difference in fluid heights to calculate the invisible pressure gap between pipe A and pipe B. Tracing the left limb, starting at point A, we move upward through liquid, distance h1. Because we move up, pressure decreases. By mapping out the depth and density of the liquid, we can read the exact mechanical pressure of the entire closed system. We can scale these same calculations up to massive real-world structures. Engineers rely on these equations to determine the exact force thousands of tons of static water exert against a dam. This section shows the formula to calculate that total hydrostatic force, denoted as F. It requires multiplying the fluid density, gravity, the area of the immersed surface, and the depth of its center of gravity. Because hydrostatic pressure increases with depth, the horizontal pressure lines grow progressively longer toward the bottom. Therefore, the resultant force doesn't balance in the middle. It acts at the center of pressure, point D, physically lower than the center of gravity, point E. To find exactly where that point lands on an angled surface, we use this final equation, H star, which incorporates the surface's angle of immersion to calculate the precise downward shift. If an engineer calculates the force based solely on the center of mass and ignores that downward shift, the uneven pressure will cause the entire structure to tip and fail. Viscosity defines how a substance flows, while hydrostatics determines how it behaves at rest. Whether measuring pipes in a U-tube or calculating loads on a submerged wall, the unifying rule remains constant. Static pressure increases strictly with depth. Try applying that rule yourself. Go back to the differential manometer diagram and write out the pressure equation for the right limb starting from point B. Working through the calculations is the only way to master the mechanics. Subscribe for our next video where we'll set these fluids into dynamic motion.